Hello, everyone, and welcome to the Hyperthesis podcast, episode 29. I'm Patrick.
I'm Pheely.
And I'm Liam.
Today we have a very interesting episode for you. But before we start, I just want to note a quick correction. In our biomimicry episode, we talked about how fungi were used to simulate the Tokyo subway system. After reading and watching a couple things about slime molds, it was actually slime molds that were used, and they were used to compare the current Tokyo subway system, at least at the time that this study was done, versus this optimized slime mold system. And it turns out that the slime mold system was optimized. Now, slime molds aren't actually fungi. They are a single-celled organism that can take the form of amoebas, but also tend to grow and merge different nuclei into the same one-celled body. So they're pretty interesting stuff, and maybe we'll talk about them in a future episode. But for now, does anyone have an intro topic to talk about?
I do. So I was, I'll just get into it. So there's these researchers at the University of Liverpool and John Moores University, and they've been studying why people use more energy when they walk on deformable surfaces. So things like sand, mud, etc., as opposed to hard cement-like surfaces. So I guess anyone who's ever walked, you've walked on the sidewalk, or you've walked on grass, or you've walked on snow or mud or whatever, and you know that it's easier to walk on kind of hard, solid surfaces, right? That's why you're in gym class and in middle school or elementary school, you're the floor is not made out of dirt; it's made out of hard. So it's kind of like this intuitive thing, but it's interesting that these people are studying it. And before I read this article that I found, I guess intuitively I thought, okay, if I walk on a hard surface like cement, it pushes, but I apply some force to it, and it pushes back against me with some force. That's Newton's third law, equal and opposite force, and that's what propels you forward. But when you do this in sand, for example, sand is a bit more fluidy than just solid earth or cement. So it kind of deforms as you push your foot into it, or it moves around a bit. So the force that you apply, you end up having to put more into it to get the same force applied back. So that was kind of like my hypothesis as to why this would cost you more energy to move the same amount of distance that you would on a hard surface. So in this research study, so it was published in the Journal of the Royal Society Interface, this group modeled the behavior of muscles in the legs, feet, and the toes of the volunteers, and they got them to walk across different surfaces.
Well, I want to, before you spoil the results, I want to throw out my guess first. So my guess would be like the normal force, if it's hard floor, is simultaneous. Basically, when you push against it, it gives a response right back. And the fact that it's deformed, or it takes more time for the normal force to be applied, so it's basically the impulse is less, so it's less acceleration. So it's gonna take longer. It's gonna feel harder because there's like a delay in the response time of the force. That's my guess.
Mm-hmm. Yeah, and that's kind of similar to mine a little bit, in the sense that but it's interesting because we're coming at this from a very physics oriented point of view, and the answer is a little different, actually.
I'm just going to throw my prediction in there too. I think it has to do with surface area and static friction. So when you say bounce off a floor, a hard floor, you have very few points of contact, so less friction to overcome. Whereas when you walk on a deforming surface, you have a lot more surface area that's applied, you have a larger surface area in which the electrostatic forces between the surface and whatever is walking on it, you have a larger area, and so it's more difficult to overcome that force. That's what I'm gonna say.
Okay. The answer is more of like a. It has to do with that, but I think like the primary conclusion they made is that it's more of a biological reason than it is a physics reason. So yeah, so they kind of they looked at the muscles in the legs, feet, and toes of volunteers walking on varied surfaces. And previous research and evidence suggests that walking in sand or any other deformable surface requires much more work, so force applied over some distance, than walking on a hard surface. So this intuition we have by just existing is correct. Previous research has shown that. So to find an explicit answer to their question, they took 30 volunteers and walked them across 3 different surfaces and recorded their movements, oxygen intake, the muscles were recorded by sensors and all kinds of stuff. So they walked them across a hard floor, a thin foam mat, and a thick foam mat. So these aren't realistic. These aren't like they're not just taking a bunch of mud and making them walk across it. It's an idealized environment. You start off with the easier stuff, and then you move to the harder stuff. So they're starting off with just these thin and thick foam mats, and maybe in the future they'll actually do kind of dirt or mud or grass or whatever. So they got the volunteers to walk back and forth across them for 7 minutes each, and they used the data from these exercises to create simulations that represented the average person walking across each type of surface. And from this is how they found out what was going on. So why the human body needs to work harder to walk across these squishier surfaces. And the end result was that they included that as you walk across these squishy surfaces, you actually have to take longer strides, which leads to an increased energy use by the muscles in the hips and knees. So I think the way I interpret this is that if you step on something, it kind of the squishy surface moves beneath your feet, and you have to like subtly shift your balance to account for that. And by doing that, you end up taking larger steps. And I think all these other effects we talked about, like the fact that you're actually putting energy into deforming the surface, and the fact that it's taking long, you have to put more energy in to get a normal force back out of it. I think that's all actually still there. I think all that physics kind of point of view stuff is still happening, but I think it's more apparently the main result was this more energy usage in the muscles due to taking longer strides as you walk across these deformable surfaces.
No, I don't think we're putting energy to deform the surface, though. If your body is a system, the gravity is doing that for you, right? So it's not like you.
Yeah, but you're putting a little in. You got to you're pushing on the ground a little bit, and if you're pushing, like if you're standing on like I guess you think of it like if you're standing on mud, I don't know, like when I walk through mud, I notice my feet go deeper than if I just like step in it and stop moving, I guess, because instead of just going straight down, you're putting at an angle. I don't know.
Yeah, but are you putting in effort to dig the mud, or just let gravity roll, try to push up?
Well, I guess when you walk, you're putting in effort. The force isn't perfectly vertical. It's not just gravity. You're putting in some horizontal force to move you forward, right? So you are putting in some kind of energy when you walk.
Yeah, you push backwards, right, for the friction.
Yeah.
So in this is just like a damped system in a way, right? It's just like it's like in water. You walk, not on water. You have like let's say the height of water, like you walk through water with let's say 10 centimeters. When it's flooded, you can kind of feel the little bit that like you're actually putting force backwards because you can see the ripples of the water. I think biomechanics are quite interesting. I wonder if they actually, like how you look at it to like the muscles, because when you walk, the revolution, it's called the periodicity of it is like there's a certain amplitude to it, and when you walk into the deformed surface, it's increasing that amplitude of every stride. I think that's one of also what they talked about, I guess.
Yeah, so there's this previous theory that they actually disprove in this. Well, according to their research, that they disprove. And that's the it's one of the most common theories actually that people suggest as to why you put there's an increased energy usage when you walk on these deformable surfaces, and it's due to interruptions in the pendulum motions that arise as people walk or run. So if people walk or run, you can maybe treat it like a pendulum in some sense, and that was one of the leading theories as to why it costs more energy to walk on deformable surfaces, because somehow by walking on them, you're deviating from the typical human pendulum motion to a new one, and that would cost energy. But they did not find that in their study. They said they found no such interruptions, based on the real world data. So it's kind of interesting that, like, I always think it's super interesting when in every day when scientists take a closer look at some really like trivial thing like walking. And you'd think we know everything about this by now. This isn't rocket science, right? Like, but I think it's pretty cool.
Yeah, I don't know about the exact research or what they claim, but you know, well, to not be interrupted in a controlled environment, sure, but if you walk on a footpath and then step onto a foot deep mud, you saying it's not interrupted? Come on.
Oh, okay, yeah. I guess they're not talking about like quicksand here. They're talking about like like more like sand type things. But even then, like a foam mat is still quite different from sand. And I think walking in sand or mud is, yeah, it's gonna just depending on what it is. Because like I've walked on a beach before, and it's not perfect. Like sometimes there's holes, sometimes there's bumps, and you got to kind of like shift the way you walk a lot of the time to not fall over.
Just to, I guess, add an extra thing onto this. I remember there was a research study that happened a couple of years ago, but it even looked at the different ways we walk in different types of footwear or other shoes, or yeah, I guess footwear, where if you're able to flex your foot, you're actually using less of a muscle contraction than if you step with a flat foot. And so that muscle contraction, especially like along your thigh, um, there's more of it happening when, say, you have a very hard bottom surface where you can't flex your foot. And it went on to essentially explain why skaters have nice butts, because
Yeah.
the skates are quite rigid, and so when you press with the skate, it's activating more of the muscle, or at like a higher activation than with a flexible foot, and so you're actually able to develop those muscles quicker if you are walking with a rigid foot rather than a flexible foot.
Yeah, it seems that the study definitely was kind of like the simplest case scenario, and there's a lot of stuff they could do in the future, I think. But I still thought it was interesting that I always like these topics that are kind of like, I don't want to say they're silly, but they're topics that you think would be obvious, but aren't necessarily.
Yeah, it's interesting how complex biomechanics is, and I guess how physicists and engineers and other researchers try and simplify the complex human body into these simple systems.
Yeah, and also it looks simple too. And I was thinking about, well, have you tried like doing push-ups on like a deformable surfaces? Those are difficult because you try to push force, and in a way you deform it, but it's like it feels like it's not going anywhere. Right? Like you have to put more force, try to find where is harder, or when it's compressed enough so that to give the normal force back. And yeah, there must be some interesting physics there. That's like, well, how does body compensate, and is that like detriment to growth in terms of muscles? And because like like you don't see anyone recommended do you push up on like a mattress. It's like, oh, it's really, if it's really soft. So maybe there's some people doing research on that, but let's move on to our main topic.
Yeah, so our main topic today was actually suggested from Reddit. So we made a post, I believe it was on the Ask Physics subreddit, and we got a couple good suggestions from that. And we'll be exploring the first one today, which was proposed by MC2222, So if you're listening, thank you very much for your suggestion. Um, and today our topic is how light travels through matter. Um, so we're going to try and dispel some myths about how photons are absorbed and re-emitted while traveling at the speed of light between atoms. And there are a lot of misconceptions and also a lot we still don't know about how light travels through matter. This is a very interesting topic, so thank you to MC. Is it 222 or 2222? We seem to have two different versions in our notes.
That's a typo on my part. I think
Okay.
it's all the twos, 4 of them. I'll
MC
double check.
squared.
Yeah.
Okay, I see.
MC squared.
Cool. But yeah, this is an excellent idea. So I think let's get into the discussion.
Yeah. So when I read the suggestion, I'll quote what he wrote, or she. I'm not sure. I'll quote what they wrote. How light travels through matter. It'd be good to dispel the myth that photons are absorbed and re-emitted while traveling at the speed of light between atoms. Many people think that this absorption and re-emission delay is what causes the slowing of light and matter. End quote. So it turns out that's not the case, and we'll get into that. But there was a lot of really good suggestions. So we made this post asking to see like what the physics community is kind of interested in, and there was a lot of good suggestions that we'll come to in the future. But a lot of them are very like complex cosmology-esque things that the three of us don't know a whole lot about and actually have to do proper research on. So this topic I actually already knew a little bit about. So I said, okay, this is a good one. So there's two questions that we're going to discuss, and the first is when light goes through a medium, it seems to slow down. Why is this? And the second is why does light change its trajectory when it by some angle when it travels through a medium? The second one's known as refraction, and you learn about that in high school physics typically. And it turns out there's about both of these kind of problems. There's a lot of misconceptions, and even amongst physicists who are experts in their respective fields. So if you don't know the answer to these questions, don't feel bad about it because most people don't. It turns out, and they're questions even the experts struggle with. So this topic also actually came up in a previous episode, I think, and I ended up going and looking, and I found two good kind of YouTube videos that describe this phenomena. So if you don't think we describe it well enough, go watch those because they certainly do. And it's this YouTube channel called Fermilab YouTube channel. So Fermilab's it's America's particle physics and accelerator laboratory, located in Illinois. And they have one video titled "Why Does Light Slow Down in Water?" and then kind of a follow up, "Why Does Light Bend When It Enters Glass?" A video called that. And so it talks about these common misconceptions and what's going on with the physics. So to start, if you have a laser pointer, say like a red laser pointer, and you in a vacuum and you shine it through some rectangular block made out of glass, the light traveling through the vacuum moves at the speed of light, which is about 300 million meters per second. It's pretty fast. All right, so as the light hits and enters the glass, its trajectory deviates or changes by some angle with respect to the surface of that glass. And this angle depends on the properties of the medium which the light's traveling through, so the properties of the glass. This kind of property is known, this bending of the light is known as refraction, and it's an experimental fact, and mathematically it's described by something called Snell's law. So again, this is stuff you kind of typically learn in high school. Some of it, you learn a little bit of it in high school physics or introductory physics courses in university. And it describes kind of the ray optics theory of it. So the properties of a specific medium, so this glass block we're thinking about, they're characterized by a number called the index of refraction, which is usually denoted by the letter n. And the index of refraction is simply the ratio of the speed of light in the vacuum to the apparent speed of light, that the apparent speed that light travels through. So as this light travels through the glass block, its speed will seem to change. It'll seem to actually slow down. This ratio of the speed v divided by c gives you your index of refraction. So in the vacuum, the index of refraction is 1 because c divided by c is 1. In air, it's approximately 1. So in air, light pretty much goes the same speed. It goes a little bit slower because air is a gas and it's pretty dilute compared to a solid material. Window glass, some other examples, has an index of refraction of about 1.5. So in glass, light slows down a good amount by about 2/3 the speed of light. And in water, the index of refraction is about 1.33. So the speed of light is about 3/4 of what it normally is in water.
I will just say, mainly because I just taught this morning, but this is for visible light, or in this case, a red laser pointer. So w- I, we might get into this a bit later, but different media will actually be opaque to different wavelengths of light. But just keep in mind that this is all for visible light that's able to pass through glass, or through water, or through the atmosphere quite easily.
Yeah, I guess it depends on what light you're using and what medium, because like UV light doesn't pass through glass, for example, typically. But assuming you have some kind of light that can pass through some material, and again, it's all very contextual, but yeah, just think of visible light through glass for now, or water, or something, right? So this refraction, the light kind of changing its speed and changing its angle as it enters something. It's why, for example, when you're in the shallow end of a pool, and there's something on the bottom of the pool, you might reach down and try and grab it, but you could have a hard time finding it. It's because what you see through the water, it's actually kind of an illusion in a sense. It's if you see like a ball at the bottom of a pool in front of you, its position will look different to what it actually is due to the light that comes out of the water into your eyes being deviated by some angle. So, when light enters a medium, what's first off this first question, why does it slow down? What causes this? But what's more interesting, in my opinion, is that if you have this block of glass and you shine light through it, it hits the light, it slows down, but when it leaves the light, it goes back up to its original speed. You might intuitively think, well, once it's slowed down, it's slowed down. Why would it jump back up to its apparent speed? So what causes this? And it also, again, when it enters, it changes its angle, but when it leaves, it goes back on its original angle. So the angle unchanges. So in those YouTube videos I mentioned, there were some really good animations and pictures, which I can't show you here because it's a podcast. So again, I'd recommend go looking at those if you want kind of a pictorial representation of what we're going to talk about. But to start, let's talk about some of the wrong ways in which people think about how light travels through a medium. So these are theories that aren't correct, essentially. So the first misconception, you may think that light actually, so as the light enters this medium, you might think that it bounces around off all these atoms. So it scatters off the atoms that make up the glass. And when it comes out the other side, because of that, it's traveled a longer path than it would have if it were just a straight line. So it seems to have slowed down. And like this is a pretty good first guess, I think, in my opinion. It makes some sense. The light bounces around, it takes longer. It explains why it slows down when it enters the medium.
Okay, I think you have to set a little premise. Are we looking at light as particle or wave? It sounds like you're talking about particles.
Yeah, that's
light,
it.
light bouncing around.
Yeah, well, that's
Well,
spoiler alert. That's the solution to the problem. Is everyone thinks of it as a particle, and it gives you things that don't make sense. So you have to think of it as a wave.
yeah, because I was thinking like, well, if you think of it as like electromagnetic wave, E induce B, then induce E and B, and then it makes more sense that there's some certain like dielectric constant in the material that kind of dampening that speed of induction
Yeah.
almost.
Well, there's the
Yeah,
episode.
anyways,
We're
yeah.
done. There's the answer.
Really?
Well, like essentially, yeah, it has to do with waves and fields and inducing fields, but we'll come to that. I want to go through kind of like what you might guess first. And the first a lot of guesses are what happens if you think of light as a particle. So light has this weird property that you can think of it as a particle and a wave, and you tend to, depending on the situation, some descriptions work better than others. That's a pretty common thing in physics. So this first one is like you're treating the atoms in the glass that make it up, or the molecules, as particles, and the light is a particle. So like these little billiard balls that bounce around when they come into contact with each other. The issue with this this scattering kind of explanation is that scattering is definitely not a precise phenomena. Light can scatter in all kinds of different directions, and take many different paths. So there's no way to guarantee that the light would end up traveling out of the glass in the same way that it did when it enters. So if it entered at some angle, it could come out at a completely different angle, a random one. So if scattering were the explanation, the light wouldn't follow a single path that we see in experiments, and it would instead spread over a range of paths, and angles with the glass, and with different velocities, not just one change velocity. Some photons would scatter over longer distances, and some would scatter over shorter distances. So the effective speeds of each one would kind of depend on which one you were looking at. The second misconception is that instead of scattering, that light is actually absorbed and re-emitted by atoms many times during its journey through the glass. So atoms can do this thing where if you hit an atom with a particle of light, so a photon, it can actually excite that atom's state. It can cause the electrons in the atom to gain more energy, and in this process, they've absorbed this photon, but then the atom wants to return to its original kind of lower energy state. So the electron that's been excited will jump back down to its lower energy state, and the atom will re-emit the photon. That's called absorption and emission.
Yeah, I think an argument against that is also like, an atom or like a molecule only absorbs specific wavelengths or energy of the photon. So, then a lot of things not going to apply because you can see clearly from, well, astronomers do this all the time, right? They get light from the outer space and they look at the spectral profile, like, oh, what wavelength is absorbed, and they can kind of work out the composition in the stars or the planets from those kind of absorption or absorption spectra.
Yeah, so exactly right. Like atoms, they have this is like what quantum mechanics tells you, is that these energy levels are discretized. So it's not a continuous there's not a continuous range of energies that these electrons in the atom can hold. You need to put in a certain amount of energy for the electron to jump up to its next excited state. But similarly, when the electron jumps down, it can only emit photons with a specific energy. It can't emit with any kind of energy. So that's kind of like one argument against it. And the other is that even if you shined light through a material with the right kind of frequency, so it had the right energy, so that these atoms could absorb and emit it over and over again as it went through the material, the total time the photon would spend being absorbed by the atoms would account for the longer time, that the slow and the speed of light. And again, it's kind of like a sensible guess at first, but it's wrong. So when an atom absorbs a photon, it doesn't remember which direction the photon came from, so it'll emit it in a completely random new direction. So the photon will randomly travel through the glass, essentially, if this explanation were the case. And again, in experiments, you can do it yourself. You can shine a laser through like a prism, or a monochromatic laser, so like a red laser pointer through a prism, and it'll go in, it'll change its angle, and it'll come out, and you'll see like a straight line the whole time. If this absorption and re-emission process was true, you'd actually see a lot of dispersion happening. So as the light entered the glass, you just see this kind of glowing effect coming out of the block, like the circular glow happening within it. And again, that's not what we see in experiments. So neither of these explanations fit the actual experimental data, and that's kind of the most important part of physics, in my opinion. There's all these famous quotes about how if you're doing physics and it's not matching the data, then like what's the point, right? So, and again, even if in like a material there is absorption and emission happening, some like a little bit of it, and even if there is a little bit of scattering, it's not the predominant effects that are causing what we see in experiments. There's not enough happening to account for what we see. So what's happening? And it's exactly what you said earlier, Pheely. The previous two explanations that were wrong, they treat light as a particle, but the real explanation requires you to describe light as a wave. So light, it's an electromagnetic wave. It's an oscillating wave. So a beam of light or a photon will have some associated wavelength with it. And this will determine its color or energy or frequency. Same thing, just different way to look at it. So, for example, a red laser has a wavelength of around 700 nanometers, which is lower in energy than, say, a violet laser, which would have a wavelength of about 380 nanometers. And when waves have a property that they interfere with each other, so you can superimpose them. So when waves overlap, they can constructively interfere, so they can add excuse me, they can add together to create a bigger wave, or they can deconstructively interfere and cancel one another out so that there's no wave. And realistically, they usually do a combination of the two, so they interfere with each other. And if one wave has one speed and it overlaps with a second wave with a different speed, they'll combine into this third wave with a new third speed, and that will actually differ from the speed of the initial two waves, which originally before they interfered. So with that in mind, you can completely describe how light passes through a medium. So as this beam of light, this electromagnetic wave, enters the glass or some medium, it oscillates because it's a wave, and it causes oh my god, sorry. It causes the electric charges within that glass to actually oscillate themselves in response, because electric charges will feel a force due to an electric field that's described by electromagnetism. And as these electric charges oscillate, we actually know that moving electric charges produce their own electromagnetic fields. So the light enters the glass, it oscillates these electric charges. The oscillating electric charges create their own electromagnetic field, so they create their own wave. And that wave they've created actually interferes with the original electromagnetic wave of light. So that's what actually causes this new electromagnetic wave within the glass has a new speed, which is slower than the original one that entered it. So that's what's going on with why does light change its speed when it enters a medium? Why is it slower in a medium than in the vacuum?
Yeah, well, that is interesting. Well, I think one of the thought experiment or possible experiment that I just came up with in my head 10 seconds ago was that, well, remember the double slit experiment, right? Light behave like wave until we observe it, and then observe it at the slit. It's like, well, where are you? So what if we find a way to observe it in a medium, or like right before it goes in a medium? Would it still behave like it's you expect it to be, or would it start behaving like a particle? And like, what would a particle be like? Light particle behave in a medium then? If you basically force them to not be away, well, force them to act as a particle by just observing and collapsing its wave function, basically, and force it to be a particle. I don't know if anybody have done that. Maybe not in the textbook I've read, but I have no idea.
So, not so much with light and with photons, but they have done, I guess, similar experiments as to what you're describing with electrons, because electrons are also particles and not particles, similar to how light behaves. But they're of course massive, and so they have slightly different properties. But if you shoot them fast enough, they behave more like a wave. And they've actually tried experiments like this where they've refracted electrons in a medium. I can't tell you the results of any of these studies, but it's been done, I'm sure, with electrons, which are close enough to light.
Well, my get for the double slit experiment, right? You can try and do clever things, get around it, and it turns out that quantum mechanics will fight you. So if you try and be clever and kind of measure which kind of slit the electron went in for the double slit experiment, then you get rid of the quantum nature of the system. And I think in this, something similar would happen if you measured the electromagnetic wave right before it went into the material. It would behave as a particle within it before it came out. Maybe, I mean, I'm no expert. There's probably a lot of stuff I'm glazing over. But that's kind of my guess, I think.
Oh, well, how would a particle behave in the medium? Do it just bounce off We just not see light go through medium at all once we observe it right before it goes in.
Well, it would, those previous things I talked about that don't properly describe how light travels through a medium, they were all kind of particle descriptions of it. So maybe it would behave like that. Maybe it would just kind of go. I don't know. Actually, that's a good point. It might go through. It might scatter a little bit. It might be absorbed or emitted a little bit. But other than that, I don't really know.
Yeah, because it's gonna be a little weird, right? Like, oh, all these things we do, right? Well, imagine you have a block of glass or something, and you shine the light through, and you can see the light it's going through the glass, and like, well, I'm gonna put the detector in front of it. Now the light is gone. Like, well, is it gonna be gone, or is it still, or is it just because we put a detector in front of it? Maybe actually it's hard to detect light. Like, well, how is it going to behave? Is if I look at the crystal, is it going to still be light in it, or is it going to be just bounced off? I have no
I
idea.
also always get confused about this kind of stuff because, like, if you shine light through a brick of glass, like we've done this before in like undergraduate physics labs, like I think those are pretty classical systems because in quantum mechanics, when you say something, like when you measure it, it's just a fancy way of saying you interact with it. And in the classroom where I have this block of glass on a desk and I shine a laser through it, it's at like room temperature. There's a lot of thermal interactions happening. Like I'm touching it. There's light coming out of it that I see. I can see the refraction. I can see it going through the glass. I can see it unrefracting as it comes out. In my mind, I'm like, surely this isn't like. Surely it's like I don't know. Would it be a part? I get confused over this so much, but surely it's not some quantum thing happening here. But it definitely, like, I always got confused over that kind of stuff. I don't understand it well enough.
Well, I feel like even these are based a lot on quantum mechanics, but what's really happening at room temperature is not exactly quantum mechanical.
Yeah, like like it's there, but it, there's wave functions
Yeah,
being collapsed consistently because of all the interactions with the environment, right?
yeah, and also like what's it called? Um, the scale, the temperature too. Like well, we describe these by like classical electrodynamics, not quantum mechanics, right?
Hmm.
Like oh,
True.
and
Yeah.
also well, some people could say like oh, everything those things are kind of based on quantum mechanical nature of the system, but well, we're not working on let's say the quantum limit. So do those things apply?
No, that's a good point. Actually, I think it doesn't because yeah, we're working with classical electromagnetism. So the particle picture is kind of like the particle picture of light's a quantum picture, and the wave nature is kind of like the classical picture. And the class like it they're both related, but when you go down to like second quantized theory, so quantum field theory, that's where you have like that's where you have a quantized electromagnetic field, right? So if you just treat it classically with Maxwell's equations, electromagnetism, then I don't think anything quantum's happening. So if you look at like I don't know if you can meaningfully say I measured this particle of light before it entered the glass block if you're working with a classical electromagnetism.
So actually, to move on from the topic a little bit, so now we kind of answered why it slowed down. So why does it refract?
One last comment is why this also explains why as the light leaves the block it re-speeds up because when it leaves the block there's none of these electric charges in the atom, so the electrons. So there's no more oscillating field being produced by the light. So once it leaves, it goes back to its original shape. It's no longer interfering with this wave it produced within the glass block. So it jumps back up to its original speed of light.
Just to interject just quickly for people who might be a bit floundering in this conversation of should light be treated as a photon or as a particle or a wave? Just we mentioned Maxwell's equations. We haven't really gone too in depth with electromagnetism, but Maxwell's equations essentially describe electromagnetism in general, and we can derive from that properties of light as a wave from those very few equations. So we'll have to do some more on electromagnetism soon, just to, I guess, provide a lot more background knowledge about how we came to know all this electromagnetic stuff and what we mean by classical light in an electromagnetic sense versus this modern quantized light.
I'm studying for my comprehensive exam right now in like 2.5 or so weeks. And there's also this really nice analogy between electromagnetism and Bose-Einstein condensation, which I think is really cool. Because they're both like the mean field limit of a second quantized theory, but I won't get into that.
Whatever that
Yes,
means.
for the physics,
But,
like we don't have a specific skill level here. We try and keep it simple for everyone, but every now and then I like to toss in some physics for those who know it.
But anyway, so we know kind of what happens with light and it's slowing down in a medium, but what's up with that angle change?
Yes. So none of this really explained. It explained why it slows down, but none of it really explained why it changed its angle when it transitioned between media. However, and again, there's a few misconceptions about this, and I'm not going to get into this topic as in depth as I got into the last one. But I'll kind of I won't talk about the misconceptions. I'll just kind of go straight to the answer this time, for the sake of time. So it turns out that the only way to properly describe why light deflects at an angle between mediums, it's again to treat light as an oscillating electromagnetic wave instead of a particle. So this means that one needs to deal with Maxwell's equations, which are these equations that govern they describe these electromagnetic waves in the vacuum or in media. And essentially what happens, without getting into the math, is that as the electromagnetic field, so this light, it hits the medium, it interacts and it interacts with the atoms and the charges in the atoms, and it changes the electromagnetic field within the glass like it did before, similar to what we already described. What ends up happening is that these reordered charges, they end up creating a counterbalancing electromagnetic field, which reduces the total electromagnetic field within the medium. And again, this is kind of rephrasing what I said. And this new reduced electromagnetic field is a vector. And this is again, you kind of have to get into the math to describe this a little bit, but vectors have components. They can be broken up into basis vectors. So you can say, oh, I want to travel to my friend's house. I have to go north 5 kilometers and east 2 kilometers. What you've done is you've taken a straight line, you've broken it up into two different lines, one that goes north and one that goes east. So you're doing something similar here with this new electromagnetic field that's been produced within the glass. So this new smaller electromagnetic field, which can be broken up into its vector components, it'll actually only be smaller along a certain component and not the other. So resulting in an angle change of its direction of travel. And so this isn't a very intuitive answer, and I don't think there is a very intuitive answer. You kind of have to get into the math a little bit. And you kind of have to look at Maxwell's equations to see this. It's not a super nice kind of analogy, but essentially what happens is that you get a vector, electromagnetic field's a vector within the glass produced, but it's a different angle than what you would expect, and it causes the new vector, the new sum of the two vectors, to be different with a new angle.
Would you think that's from? Well, if you think about things, I'd like to think of things in symmetry. Like things are symmetry, and having kind of like come in one angle, it bends the angle. Is it because some kind of asymmetry or like something that's not symmetric in the equations?
Good question. Depends what symmetry you're talking about. So Maxwell's equations, they're symmetric, they're Lorentz invariant. I don't know if that has anything to do with it, but
It shouldn't.
And just to clarify, since we did talk about relativity, Lorentz invariant means it's they don't change regardless of your reference frame. So you could be traveling at close to the speed of light, or you could be stationary on the Earth, but essentially it doesn't change anything about.
They'll look different, but you can mathematically like agree upon them. You can say, I know it's different from this frame, I guess.
Yeah.
Everyone who's in an inertial frame will agree, or Anyone who's in a Lorentz invariant frame will agree with you, kind of thing. Anyway, sorry, I didn't want to get into that, but yeah, the answer for why it bends is a bit different. But if you've done some vector calculus, you can understand it. I think just that your new electromagnetic field that you produce, it's a vector, and its direction will change the original direction of the light by some angle. Because when you sum vectors, you got to sum their individual components, and the new components might add together to a new angle, essentially, give you a new angle. And there's this really cool, excuse me. And I'll say one more thing about why light changes its speed when it enters a medium. It's this kind of like fun analogy I saw somewhere online at some point in my life. I wasn't able to re-find it, but you can think of it like a car driving down a road, and the car represents your light, and the road represents the medium or the vacuum that you're traveling through. So if the road's completely smooth, like fresh paved road, the car's gonna go very fast and it's not gonna interact with anything. So it's like light traveling through a vacuum. But if there's little pebbles all over the road, the car can still drive down that road fast. But every now and then, it might ding a pebble, it might interact with it or something. So it's like light traveling through air, something that's not a very dense medium, and it doesn't really have too much of an effect. And maybe it'll hit a pebble and scatter off of it, but it's not going to change its speed that much, and it rarely does. However, if you're driving on a gravel road, these little tiny individual pebbles, you slow down your speed on a gravel road overall, but it's not like you're bouncing off of every individual pebble that you hit. It's not like a car is being scattered, deflected by a pebble, right? It's kind of the overall net effect of these rocks on the ground slow you down in the car. It's something similar happening with light in a medium. It's not like the light's actually scattering or being absorbed by individual atoms as it goes through these individual pebbles. It's kind of the net effect of all of them as it travels through it.
One thing to note is that an atom has electric field, right? It has charge. I mean, there's protons in the middle, then allegedly,
Yes.
bunch of electrons around, forming some kind of probabilistic cloud, right? And those also emit some kind of electric field, and if it's moving, some could say magnetic field, and those interferes with things compared to a vacuum when there's nothing, or theoretically. And I think that's really important because, like, and that might also be why it will turn, light will bend certain way, because electron has negative charge, and protons in the nucleus, so the effect of the effective range that the charge can influence the surrounding is less, because it's hidden or tucked away in the middle, while the electrons around are surrounding it. So this is just my guess. It'd be like, well, because you're going through stuff which is mainly negative charge, maybe that's why things are bent certain ways compared to when everything is such a positive. But maybe not. That sounds a little too reductive, because what if you have a material just made of just nuclei, right? Like, what if you shine light to it? Would it have the opposite effect? Well, it would be weird in terms of angles, and you can't have a material you go to have a higher speed of light, right? Like, you can be faster in the vacuum. What, would it bend a different way? Who knows?
Well, this is some very interesting conversation. So if you have either a theoretical background in light, or if you have access to a laser lab and some exotic materials, then feel free to let us know about what you think of this problem. And really, if you have any input about how light passes through media in general, we would love to hear it. You can reach us if you would like to share your thoughts or possible experiments. Again, some cool experiments that could be done. You can reach us at hyperthesispodcast@gmail.com. That's our email that we check quite constantly. So if you have suggestions for future episodes, or if you have comments on current episodes, you can send us an email. You can also reach us at the Hyperthesis. We are on Instagram. And we post updates about when we will be posting episodes, along with general behind-the-scenes looks. And Liam also tends to post
I don't
some
think I've posted
good
one in a while.
memes, some dank memes, if you will. We'll have to get on that. You can also find us on YouTube. You can just search Hyperthesis Podcast, and you will be able to find our videos. A lot of work goes into, I guess, their animation, and by that I mean CPU hours. But Pheely also did a lot of work for creating those video templates and also editing the episode. So if you have any questions, comments, or concerns, you can reach out to us through any of those methods or those media, if you will. And you can also listen to us on Apple Podcast, Google Podcast, Amazon Music, or wherever you find your podcasts. We're also on Spotify, and we're based out of anchor.fm/the Hyperthesis. So give us a like, subscribe, follow, whatever you do on whichever media platform that you use. And so we're going to be ending this episode with, I guess, one of the original thinkers about how light operates and was actually able to describe its properties using mathematics. And today, I'm surprised we haven't done it yet, but we're looking at the life of Sir Isaac Newton. Now, he is very, very well known. It's a household name, and it's also the name for several different units, and there are many things in which Newton is known for. Um, I would say his genius was very hard to surpass, and maybe Einstein was the first person to truly become another household name as a physicist and a mathematician. And there are also many myths and legends about Newton, from an apple falling on his head to holding grudges against other scientists. But if we go back to the very beginning, Isaac Newton was born on Christmas Day in the year 1642. Although this date is different depending on which calendar you look at. The Julian calendar was in use at the time, which is different than the Gregorian calendar. But nevertheless, he was born in Woolsthorpe, Lincolnshire, a small town in England, kind of in the center of England, close-ish to Manchester. His father, of whom he shared his name, actually passed away 3 months prior to his birth. So he grew up without a father, and his mother's name was Hannah Ayscough. I think I might be pronouncing that right. It says a few hundred years ago. Now, she didn't actually stick around for too long before remarrying and letting Newton's grandmother raise him. Now, Newton actually didn't like his stepfather and proceeded to make several threats towards him and his mother, including burning them in their house. So a little bit of resentment there. Now, other than that, not much is known about Newton's childhood. Other than that, he studied at the King's School in Grantham, which most likely gave him a solid foundation in mathematics. There, he studied from the ages of 12 to 17 before he was removed by his now twice widowed mother, who tried to force him to become a farmer. Now, we don't know of Newton the farmer. We know of Newton as the famous mathematician and physicist. So his mother was persuaded to return him to school by the principal, who was named Stokes, but not that Stokes. This was a different one.
My recent publication has Stokes in the title, so I got a little excited there. I was like, oh.
We'll have to talk about that soon. But this was a different Stokes who was the, I guess, headmaster of the school. And once returning to school, Newton was able to become a top-ranked student, possibly as revenge towards a bully, which I find quite funny. At the age of 18, Newton was admitted into the University of Cambridge in the year 1661. There he studied for 7 years, eventually getting his Master of Arts, while also receiving a Bachelor of Arts, because at the time, science was an art. And you can actually still get your BA and MA in different fields of science, depending on which university you're at. Now, during his time at Cambridge, he studied the works of Aristotle, Galileo, Descartes, among many others. And during this time, he discovered the generalized binomial theorem, and he also began his development of calculus. Shortly after he finished his BA, Cambridge was actually closed due to the Great Plague, which was the last occurrence or major occurrence of the bubonic plague within England. And this forced him to work from home for 2 years, where he developed his theories on calculus and optics and gravitation. Now, once he returned in 1667, he was elected a fellow of Trinity at Cambridge. So that's the Trinity College at Cambridge, where he did have to assert his conformity to the views of the Church of England, but through some trickery and loopholes, he was able to get special permission from the King Charles II. Now, part of this, the reason for this loophole was because of his unconventional views that didn't necessarily agree with what the church was saying. And Newton actually, I guess, wrote responses about different verses in the Bible to try and find the science or to disprove them, which in the eyes of the church wasn't great. Now, Newton became a fellow of the Royal Society, which was a very prestigious role, at the age of 29. So for those who are under 29, there's still a chance. Sorry for those of you who are over. Before this, Newton had been touted as a genius by many different colleagues and people that he met. And he developed essentially every field of mathematics that was being studied at the time. His main body of work was the Philosophiae Naturalis Principia Mathematica, also known as Mathematica Principia or just Principia, which was a tome that he wrote in Latin detailing his laws of motion and gravitation. So this was a very hefty book, and it said that he wrote it in Latin, so only the most educated could read it. And he also allegedly made it a challenging read just because you had to have a really good head on your shoulders to be able to understand it. He also had many other publications during his life and after his death. But after his death, and to this day, there was, I guess, myths swirling about him. And one myth was that an apple had fallen on his head, leading him to come up with his theories of gravity. Now, a lot of people think this is a myth, and the apple falling on his head part most likely is, but it's said by many close contacts of his, and even maybe from himself, that by watching apples fall in an orchard, he was able to start thinking about gravity, which eventually led to his theories of gravitation. Now, there are many, many accomplishments in the life of Newton, including describing optics and how they work. And part of this is related to what we were discussing today, about how light travels through a prism. Now, I believe Newton believed in the photon as a particle theory, because wave theory wasn't really a thing at the time. But he is notable for developing the field of optics. Now, there are many other things to say about the life of Newton. After Cambridge, he became highly positioned at the Royal Mint, eventually becoming Master of the Mint in 1699, where he would spend the final 30 years of his life. So his time at Cambridge didn't actually last his whole life. He gave that up shortly after becoming Master of the Mint. And he certainly did some interesting things while being the master. This was at a time of currency reform, so they were taking in all the old coins and producing new ones, and there was a lot of counterfeit coins, and so Newton himself would disguise himself, go to bars and taverns, and try and collect evidence against counterfeiters. He then cross-examined suspects and was able to prosecute 28 counterfeiters, or coiners as they were known. Now, in 1705, Queen Anne knighted Newton. He was the second scientist to be knighted. However, it was most likely for political motivation, given that parliamentary elections were happening later that year. So it was more symbolic and to win political points than anything else. And Newton did have quite a bit of political sway. and through a report that he had written, Britain moved to the gold standard as a result of some trading that happened where silver left the country and a lot of gold came in. Now, Newton died in his sleep on March 20th, 1727. Again, different dates for different calendars, but he did die in March of the year 1727 at the age of 84, which is quite old for the time period. He was given a ceremonial burial and funeral, and he was buried at Westminster Abbey, being the first scientist laid to rest there. He died having never married, and his estate went to relatives. It is thought that he actually had mercury poisoning, which led to some eccentricities later in his life. Now, despite these eccentricities, Newton laid a foundation of physics that we still use to this day, and mathematics, which we definitely still use to this day. He also had some controversies in his life, including his relationships with Leibniz, who is also said to have developed calculus, and again, lots of controversy there, and also with Robert Hooke, whom it's said that he hated quite a bit, to the point where he burned his portrait at the Royal Society, so we don't actually know what Robert Hooke looks like. It's a mystery. However, despite these controversies, it's hard to argue that he was truly a brilliant mind, one that only comes every few generations, and his developments in mathematics and physics are still felt to this day, and it's what we learn in first and second year courses, and even further. So he's quite the brilliant mind, and we have a lot of our knowledge today to thank him for.
Definitely a strange man, but kind of the brightest minds in physics. The Einsteins tend to be strange, so it's interesting.
I should mention he also got into alchemy. So
yeah, he had some weird stuff. Like he had some experiments where he wanted to understand light and color better, so he like kind of would poke the back of his eyeball with like a needle and stuff like that. Like pretty wild stuff that most people would kind of clue in and be like, maybe I shouldn't be doing that, but he needed to know.
Yeah, definitely signs of mercury poisoning. But with that, thank you very much for joining us for this episode. We hope you enjoyed it, and have a good day.
Take care.
See ya.